them successfully really have to mimic what happens in the linear case. Only that things get simpler. We now look, well, one way, or the way in which this partial closure operator was defined was first to look for structural zeros in the Gaussian, in the linear case. What are structural zeros? Well, it can happen in general when you have a graph, say like this, minus C, C. In general, there would be a dependence induced between I and K when we marginalize over these two. But when the regression coefficients take on very special values, the paths get cancelled. And therefore, whenever you analyze a particular set of data, this can always happen. You will not recognize the structure independent of the parameters that you have been estimating or that you know. And this is a case of parametric cancellation. This can happen for particular parametric constellations, but it will not happen for the operator that I call finding the structural zeros or close path in the graph. So remember how that looked? We had an element S, and so the new version for the graph just ignores the S and replaces the minus by a plus. So instead of having a sure complement, we have the properly adapted version for the graph. And again, you can describe the whole operator by doing nothing. You leave everything unchanged except the subgraph that corresponds to M. And there we introduce an additional edge whenever there is a V. That's what this operator is telling us. So now here's partial closure for a directed acyclic graph. If we have a directed acyclic graph, we have such a triangular decomposition where there are zeros in the lower triangle, and in each row you have the regression coefficients. And if I now do 0 A on subset A on the matrix, which is an edge matrix of such a directed acyclic graph, I get a new edge matrix, also 0 ones. And every A-line ancestor in A is turned into a parent. What is an A-line ancestor? I have I, J in A, J in J, let's be a little bit sloppy, K. So all nodes, this is an ancestor of I, and if all inner nodes are along such a path, then the operator will introduce an error. So if I do that, I don't really remove anything, but that's what the operation is doing. And it has been treated totally independently of the operator that we have introduced very late under the name of finding the transitive closure of the directed acyclic graph. And it has another relation to a very, very old result. It's not a typo, it's true, 1884, and I found the right page in the book in the excellent library in Sweden. So when you have a matrix that is upper triangular and has ones along the diagonal, then this is the identity matrix, to the power R, counts the number of paths of length R. And then that this whole thing, we always need the identity matrix, that this whole thing reduces to twice the identity minus the 0, 1 edge matrix, takes the inverse, replace everything that is in it that is non-zero by once, then you have this transitive closure, or the edge matrix of the graph that has been called the transitive closure. You can find that in this book, in German of course, not very helpful, still in English in 1966.
So the script to B and A inverse, they are all triangular.
And in that case, yes, it's an example. We're looking at the edge matrix of a directed acyclic graph. It has zeros. It is a triangular matrix of zeros and ones. Ones along the diagonal, and an edge whenever there is a one in the upper part.
Beautiful.
Yeah.
Beautiful.
So now, what do we get when we apply partial inversion to all elements, not just to a subset? Well, we get the old thing. We get the inverse when we have partial inversion. So that's neat. And partial closure applied to all indices just closes all relevant V configurations. And you have to be a little bit careful then there what you are doing. But I'll describe it to you. So here are the general two important properties of partial inversion. So we have N. We partition it into A, B, and C and call capital G the union of A and B. Then the commutativity property just means you can do the partial inversion in any order you want. You can first invert on A and then on B, or first on B and then on A, or on the whole set in any order you want. And then the second property tells you if you have done the partial inversion of BC and you now do it with respect to AB, you undo the operation that you had done before on B. So forming the symmetric difference just means you have an operator that you can apply to the same subset again, and then you return your original graph. That is a property that the sweep operator did not have. It had an additional new operator to get back to the original thing. So that is a nice little property, and why we call it a generalization. Now the partial closure shares with the partial inversion that you can do it in any order on any subset of the indices you want. Just you have to do them on all, the union of two. But you do not get that you can undo the operator. And that corresponds to what I said before. When we have work with particular regression coefficients, parameters, we can sometimes this graph would, when when you compute it, do a linear regression that has this parameter and that and this and that, and you find that I is independent of K in your data. But for the graphs, that will never happen. It will introduce this edge, and by marginalizing over these two, and edges never get removed. So you have to have a good notion of what is your generating graph. If you're wrong there, everything is a mess. So and here is a very simple example, still very simple example, but it's the first proper one where we introduce both dashed lines, full lines, and arrows. So we start with a directed acyclic graph that looks like that. And if you see this graph, and somebody asks you, write down the corresponding linear system, you write down what you see up there in this form, or you write it in terms of an additional arrow that has mean zero and is uncorrelated with the explanatory variables. So y1 depends with strengths alpha and beta on 2 and 3. All the others are simple, super simple regressions. And now somebody else comes up and says, no, I don't want this ordering between 1, 2, and 3. I think these are joint responses. They cannot happen after one another. They are joint responses. I want to have an analysis where I really have YA regressed on YB. And this is the resulting graph. Well, nothing has changed in the conditional covariance graph, if it were a linear thing, and in the marginal concentration graph, because we're looking at transition nodes and we condition on it, and here we look at a collision node and we marginalize over it. So we only get informed, well, these are now the relations, no longer 3 influences 1 and 2 influences 1, but they are undirected associations between 1, 2, and 3. And then you see the other thing we also know already, we have a transition node from 6 to 2 and 1, and 6 and 5 and 3. So we introduce an additional edge for these two. Or you do the matrix stuff that I have just described to you, and some routine in R will do it for you. But this is a very special case. All I've done is split my 1, 2, 3, 4, 5, 6. N is this. Oh no, actually it's ordered. And I split it and call this A and B. But it shows you how the dashed lines, the full lines, and the arrows result when you change your attitude or your knowledge about what are single responses and what are joint responses and what are background variables and what are response variables.
Where's that? The sigma super double B dot A is...
It's the marginal, the concentration graph of YB, or the concentration matrix here, of just the margin YB, YA, YB, and the dot means you have marginalized over B. It's a corresponding thing to the conditional covariance matrix, where you subtract. It's a standard notation for marginalizing and for conditioning. So here is the edge matrix result for what I just said what you do in the graph. I have given my triangular edge matrix for the graph, and I close every A-line ancestor into a parent. And then I look at the transformation again after first finding the concentration graph, and it gives me something that I had introduced in the simpler cases already, an edge matrix multiplied by transposes. It closes all these source V's, sorry. IK closes the transmitting V's, and the last one closes the sync V's. So now, instead of going to the more general case with a generating graph that is directed in Acyclic, I'll go to the main result that has been around now for regression graphs, where you do not have to use a simple split like this, but you might have n equals 1, 2, 3, 4, 5, 6, and your A may be 1, 3, 5, and B maybe something else. There's the rest. 2, 4, 6. So any subset. And then you write it again in a way so that you have a proper partitioning. So this example now, this is a general equation for a multivariate linear regression that has a covariance matrix where not everything is 0, but there may be associations, the residual covariances of YB tilde given V, the conditional covariances between nodes in A given B and V, and the marginal concentration here. Notice we use a little thing that has been, so if I have Y mean centered and I take this particular transformation, I start with Y equals YA or Y, it's a vector. And I multiply both sides with that, and I want to find the covariance matrix of Y. Is that right? What? So sigma Y. What is the expected? I might huh?
to diagonalizing?
No, you just multiply both and take the expectation. So you take y transpose, and you get sigma and sigma to the -1, and the expectation of this guy is sigma, and it cancels. So that's what you should do. Mm-hmm. So I should start directly with that, a particular residual. Then I multiply that with that and take the expected value. Anyway, you get this feature you see here. I have the same thing sitting in the equation parameters and in the structure of the concentrations. So, and here's now what we do. We do partial inversion on this block diagonal matrix H, and partial inversion on a subset on the covariance part. And we know that after these operations, the part in the matrix, transformed matrix W, coincides again with the equation thing. So we get now the estimated, although in the population, sorry, the regression coefficient matrix, the concentration matrix of YA given B, and the marginal concentration matrix of B. So you just have the subset Y, and you look at its inverse, and that is the same as taking the joint and marginalizing over A. And this is a closed form expression for what you get for the new equations that are orthogonalized. And we've done that a little while ago. But we have so much to read, we cannot possibly know all that stuff. And now what happens to the H matrix? Well, something totally analogous, otherwise it wouldn't work. So we have an H matrix for the regression graph, which has this upper block triangular form. Actually, it has identity matrix on each block for the responses, and only a proper full block for the context variables. And it has a 1 if there's an error or a full line. And it has a dashed line if any pair is correlated, or it has a dashed line edge. If there's a dashed line edge, then I have a 1 in the corresponding graph. And now I want to use again this operator to get the H matrix for my orthogonalized equations, or more generally, they don't have to be linear. So remember, an A-line path is anything that starts from a node, ends at another, and all nodes along it, no matter what type they are within the subset A. And the interior path that I introduced before had this little form. And here we go. And if you want to start here, you see exactly the same formula that we had before for the linear regressions, only that they are calligraphic, because they are now transformations of the H matrix. So let's look what we do. We look at our graph. We have a subset that has only full lines. These are the context variables that are in V. And we have another subset of variables that are responses, or totally isolated, and they are in the subset V. And now we choose any subset of N, A, and B is the remainder. And then we work on the H matrix instead of the parameter matrix that we had before. And once we do that, we have an interpretation in terms of what we do in the graph. If I do partial inversion, or finding the structural zeros in this H matrix H and N, and I work on the subset C, then I close all C-line interior paths. I put a 1 into the matrix K and N. Whenever there is an I and a K, and the thing between it is a C-line interior path. The thing we saw before, and all lines in it are in C. When I do the same operator on this subgraph that has only dashed lines, well, then I close all D-line dashed path, V's, huh? Or D-line V's. I can do that repeatedly because the operator tells me I can work in any order, or I can say it closes all D-line paths. And then the result is it gives me the edge matrix of the graph that is introduced from my generating graph on N for a density of YA given B, and the margin, a concentration graph for FB.
So U variables are marginal
responses.
Marginalized.
Yeah, sort of. Yeah? You close all C-line anterior paths. You turn...
Very mysterious.
No, remember what
How do you interpret the P sub A pipe B? How do you interpret this?
Okay. In exactly the same way as we did it here. It is a bipartite graph between A and B. That's the language they use in graph theory. It has two subsets we are not interested in, and here it shows just the arrows that have to be in there. And sigma AA given B, when it's calligraphic, it is the edge matrix that contains only dashed lines.
Yeah.
And the other is the edge matrix that contains only full lines. So it's exactly the same that we did in this sampled case. Just a little more complicated looking because we are solving a more complicated problem. And the interpretation of these weirdo edge matrix products, well, if we look at the pieces separately, they have a very neat, simple interpretation. I told you that we are closing beforehand all anterior paths and every path in the subgraph that has only dashed lines. But then if I really want to get to the conditional distribution of YA given B and the marginal of B, we have to do a little bit more. And there we can translate these these products of edge matrices into simple language in the graph. So we introduce a new one in the edge matrix or in the graph, an arrow, when there is a path that starts in B and ends in A, and it is of this form. So we are conditioning on B, that's a collision node, and we are marginalizing over A, therefore we introduce, it's an active path, and we introduce an arrow, because that thing remembers the edge ends. YB there was a full line, and at YA there is a arrow, so it remembers it. And if we have that matrix product, it generates a dashed line. And that matrix product, it is generalizing what we saw here as a collision node. Because it is really looking at these things. And we only need to look at subsets of 4 nodes because we have done the closing of other relevant paths beforehand. So if you want to describe this whole procedure of what is induced for another regression, well, if you're just interested in the regression, stop with the upper thing. That's it. If you don't want to know what the residual covariances are implied and the concentrations. But it is a full description. And it gives me much more than we used to have so far when we were looking at graphs only as independence graphs. Remember, I want to use dependence graphs, dependence space, and edge minimal graphs. And now I can not only answer a question, is alpha independent of beta given C, but I can also ask, what does a graph and the corresponding generating system imply regarding the dependence? So I take alpha, beta as the 2 things I'm interested in. C is a conditioning set. M is the things that I'm ignoring or marginalizing over. And so I want to know what happens in the marginal distribution between alpha and beta given C. And the answer is super simple. You get an edge matrix. It has only zeros between alpha and beta. It's a subset of the matrix that we have just computed before. And if that edge is empty, it's 0, then the graph that really has dependences whenever I see an edge implies not only marginal independence, but marginal independence implies also that the edge matrix is 0. So it's an only thing. That is, you asked before, why do you worry about composition, intersection, singleton? Well, I get to these much stronger statements.
So you work with the full model structure, and then you just look at your interest area, alpha and beta.
And I can not only conclude something about the induced independences, but whenever there is a single one in my edge matrix, then there's a dependence. So my generating process implies a dependence. And for that, to conclude that, we need these 3 properties. Traceable regressions are defined for arbitrary types of variables. They model sequences of joint or single response regressions. We are allowed to use a graph to trace development. We can decide on implied independences and dependences, and they are a standard subclass of graphical Markov models and generalize what Matthias Tritten had studied a little while ago. So I wanted to end all this with some history, enough technical stuff. So graphical models, where do they come from? Well, graphical models combine 3 very powerful tools developed more than a century ago, essentially. Well, 90 years and more than a century. There was Sewell Wright, a geneticist, who used directed acyclic graph, of course without calling them that. He just used systems of linear equations in standardized variables. The nodes in his graph present variables and arrows linear dependencies. And then he computed the implied correlations from this process and compared it with what he saw in the data. So he was far ahead of many statisticians who developed goodness of fit tests much later, 30, 40 years later. Andrei Andreevich Markov is known because of the Markov chains, but more generally he had the idea that what looks very complex can possibly be much simplified by introducing the notion of conditional independence. And Gibbs was studying gases, and he used undirected graphs to describe the complexity of a system in terms of the number of nearest neighbors that he had, and he used full lines to represent the undirected associations. And here are these 3 characters who lived a little while ago. The pictures are not so fantastic. Sewell Wright turned almost 100 years, was at the University of Chicago. I still was in writing to him, and he insisted you always have to use standardized variables, otherwise everything is nonsense. So Andrei Andreevich Markov was at St. Petersburg, and Willard Gibbs studied in Göttingen and then was at Yale University. So graphical models, when did they start? Well, they came to life not very long ago, with some works that started by works in biometrics, 1975, in the Journal of the American Statistical Association, in the Annals of Statistics, then by Darroch, Lauritsen, and Speed, and in Biometrica, and the Scandinavian Journal of Statistics. They were the first graphical things that were defined. And they were at the beginning all undirected models. And the full line models were those that were best understood. And they are now called concentration graph models, even though Arthur Dempster, who studied them first for Gaussian distribution, gave them the name covariance selection models. I have not the foggiest idea why he called it that way, and never found out.
Confusing. It's confusing terminology.
So for the joint distribution of discrete variables, the concentration graph models really correspond to the log linear model, and it was John Darroch, Stefan Lauritsen, and Terry Speed, who recognized that in 1980. But the work beforehand, well, it started actually with Bartlett in 1936, who defined interactions in contingency table. Then the marvelous paper by Martin Birch in 1963, Leo Gutman in a whole series of paper, Rolf Sundberg from Sweden, and then Bishop, Feinberg, and Holland with their mammoth book of 380 pages, or no, 400 maybe. And then now the covariance graph models were actually studied by our still alive grandfather of multivariate analysis, Ted Anderson, in papers 69 and 72, so around the same time. And he also studied Gaussian distributions and talked about hypothesis linear incovariances. So these are really one type of covariance graph. Now we speak of concentration graphs even for all types of other distributions, because they always mean when you see an edge now given all the remaining variables. And so that is how you interpret also an element in the inverse of a covariance matrix, the concentration matrix. The covariance graph models are called covariance graph models because they correspond to zeros in a covariance matrix. And of course, if you want that to be meaningful, you must have a distribution that can essentially be described in terms of pairwise dependencies. Otherwise, this whole thing is nonsense. And that happens when you look at conditional covariance graphs in these regression things. In the meantime, machine learning people try to use covariance graph models as a search environment, and they are not aware of things like you can have 3 pairwise dependencies and there exists no joint distribution for it. So, results for reading all independencies of directed acyclic graphs. Well, this is the so-called Markov, global Markov property. There was a path-breaking formulation by Judai Pearl, Geiger, his students at the time, Geiger, Verma, with him together did a proof in some machine learning journal, which I forgot, and Lauritsen had at the same time a proof in the same journal where he reduced the formulation, gave an equivalent way of reading independencies of a directed acyclic graph by reducing it to what was known for undirected full-line graphs. So there is separation between A and B if every node along a path intersects C. That's a simple type. And then we introduced an additional form of separation using these edge operators, and well, I don't think anyone has picked up on it. So I have introduced you to the question, I have a generating process, somebody else is working with a subset YA and YB, and of course I can do that then for a whole other regression graph in sequence. So this I call an independence or dependence predicting graph. But we can also ask, can we construct a graph that is in contrast to directed acyclic graphs and to regression graphs, still the same type of graph when you marginalize and condition? You get outside the class with directed acyclic graphs sometimes. And there are 3 answers. One is called marginalizing conditioning graphs by Jan Costa. And it's a very general definition, but he didn't study really whether there are any parameterizations that go along with it. And the maximal ancestral graphs are a beautiful formulation when you're only interested in dependencies. And well, the summary graphs that came to life not too long ago have the additional feature that you detect with them direct and indirect confounding when you have a proper generating process and you marginalize and condition. And a beautiful comparison of all 3 is now available due to Kaiwan Sadecki It will appear either in the electronic journal of statistics or the electronic journal of probability. I forgot, one of the two IMS journals. But all these results are based on something that David Cox, Jutta Perl, and I did some time ago, where we designed these 10 types of induced edges. And the important step is to prove that if you combine these things in any way you want, you have a consistent system of induced edges. And that is why it took so long to get it. And the new plan is that we finish a book that we have started that describes to you all that I tried to do in 4 hours in a sensible way in a book. Okay, that was all.
Thank you.